Thanks, everyone. So I'm Jason Teutsch, and we talk about TrueBit. So in what sense am I introducing the TrueBit virtual machine? So some of you may remember last year at DevCon 2, Christian Reitwessner also gave a talk on TrueBit. So I'm pleased to announce here today that TrueBit is up on the Kovan testnet. You can take a piece of C or C++ code and run a verification game up there. All the code is up on our GitHub. It's all open source, so dig right in. And I'd also like to thank all of our, in addition to our core team, all of our open source contributors who have been making that into a reality. We are especially Sina Bibian and Harley Swick. So some of you may be old enough to remember before Bitcoin there was a thing called big data, and you could actually store stuff on your computer. You could use the computer to compute stuff, and there was even some privacy features. Well, Ethereum sacrificed all these for a property we called immutability, and that's what makes blockchains amazing. They're immutable. They have some sort of democratic equality properties to them. But so it's time to bring the big data back onto the blockchain. So TrueBit is taking this piece right here, computation, and that's what we're bringing onto the blockchain. So, and there's also a communication component to it. Just like you have the internet for big data, we're looking at something like Doge Ethereum Bridge, a way of bringing existing bridge, take the tokens off Dogecoin and put them on Ethereum and back. So that's the functionality we're talking about here. So TrueBit is a scalability solution. And in terms of the storage piece, so I'm talking about TrueBit as a scalability solution for computation. But if you look at the storage situation, there are a lot of projects already looking in that space already. Most of them are more focused on privacy than data availability, but there is interesting things going on in the storage department. In fact, there's interesting stuff going on everywhere. I guess that's why we're here. But what is it about TrueBit? What are we here to talk about today is a process which we call interactive verification. Okay, and what are we focused on? TrueBit is focused on large transactions. So we've had a few talks just recently about sharding. So TrueBit is not going to assume that you can take your transaction set and break it up into smaller pieces. You have a massive transaction that's coming in, and you have to process it. So that's what TrueBit is all about. Okay, so what's the problem? Well, what are we trying to solve here? I guess I don't really have to tell this audience what a smart contract is, but I do want to point out a sort of critical property of the smart contract is that they only, this sign at the bottom, which you can see now, says small computations only. You're not running computations that run for hours or even minutes. I mean, they don't even run for seconds. So that's what we mean by scalability. Computations that actually run. So the length of the computation you can run is bounded by Ethereum's gas limit. So the obvious thing, let's get the elephant out of the room, why don't we just dump the gas limit? So so what is the gas limit? Ethereum meters smart contract storage and compute resources with a measurement they call gas. And the gas limit is the maximum amount of gas that you can allow per block. It's not per transaction, it's per block. And so why do we have the gas limit? That's a question. So reason A, is it because every miner has to replicate every Ethereum computation? B, it's because removing the gas limit would leave Ethereum vulnerable to denial of service attacks. Is it C, because the gas limit helps incentivize transaction verification? Or is it just that Vitalik Buterin secretly doesn't want Ethereum to scale? Well, I think we can quickly cross out D because it's not a secret anymore. I told this same joke a few weeks ago at CESC. So now what I do want to do is convince you that C is, well, I say all of these answers are true, but C is more true than all the others. So this is what I want to convince you in the next 3 slides, that C is actually the right answer to this question. So let's see what happens without the gas limit. Okay, so no gas limit. You have a guy with 2 pointy horns comes in with a heavy transaction. He incentivizes it nicely, so someone is bound to pick it up. You put a nice big transaction fee. So a miner comes in, mines the block. He says, sure, I'll include that because he's got an incentive for it. And what do the rest of the miners do? They just get like completely confused, right? Because why are they confused? So let's look at a little bit into their confusion. So what are they confused about? So this is actually a principle which we call the verifier's dilemma. So in the case of a heavy transaction, what should a rational miner do? Rational miner being somebody who likes to earn more ether. So number 1, skipping verification affords an advantage in the mining race. So therefore, he has a reason to skip the verification. Mining on the wrong chain, on the other hand, means that other miners will ignore the found block. So therefore, you should skip therefore you should do the verification. So it should be clear from looking at these 2 statements that rationality doesn't actually help you decide what to do. So the miners want to do whatever other miners are doing. So that's the verifier's dilemma. So what is TrueBit? TrueBit is a solution to this verifier's dilemma. It sort of makes it so we put everything off chain, so you don't actually have to deal with heavy transactions on chain. What we've sort of observed in blockchains, and this is kind of the miracle of the whole thing, is that miners are willing to do a small amount of work for free, and then you don't have a verifier's dilemma. So here with TrueBit, we are going to give Ethereum a computational boost by doing the heavy work off-chain. So the goals of the protocol is that anyone can offer a reward for performing a computational task. Anyone can solve a task in exchange for a reward. The protocol, most importantly, guarantees correctness of solutions. And here by anyone, I mean anyone. That means a smart contract, pseudonymous identity, or the bots that came up in the earlier talk this afternoon. And so if you want to say formally, what is TrueBit? It's an Ethereum smart contract. That's one part of it. But it's also a new off-chain architecture. So I'm going to walk us through these 2 pieces in the remaining time. So let me try to explain let's look at the architecture piece first, just as an overview. So TrueBit is a unanimous consensus algorithm. Unlike Ethereum, which you sort of have majority vote on the miners, people say like this, anyone in TrueBit can challenge a computation by taking it to court, so to speak. And who sits in the court? Well, it's your miners from the Ethereum network are sitting in this court. They're always right, but they have very limited computational bandwidth. As we just see, because of the gas limit, because of the verifier's dilemma, you're stuck with that. So what can we do? So you have a solver who comes in did a computation, and then a challenger who comes in and says, well, you're wrong. And the solver doesn't actually say, let's play a verification game. He gets forced to play a verification game. He gets taken to court. Okay? So what does the court do? It tries to pinpoint the place where they're disagreeing. So you have a solver and the challenger, they enumerate their computation states. They do all this off-chain. And then the judges are going to enforce a binary search to find the first step in the computation where they disagree. So solver says, he kicks out obviously they agreed on the green means they agreed. So they agreed on the first step because that's the input, it's just given. And they didn't agree on the end, or they wouldn't have been in the court in the first place. So he says, do you agree halfway through? Challenger says, no, I don't agree on that. So we mark that as red. Do you agree at step n over 4? Says, yeah, okay, agree at step n over 4. What about 3n over 8? So we're just getting, now these are close enough. You can actually run this one step of the computation. You can do it on chain because it's small. And it's important to note here that the computational steps have to be absolutely identical across all the platforms in order to rule fairly on the final check, right? There's no notion of one step if everybody's running a different set of steps. So the judges, we have to make sure that That's the key property of our architecture, is that all the steps are exactly the same. Okay, so what happens here? So here was the last step where they agreed, and here's the step where they disagreed. This this step was, of course, provided by the solver. So he's saying, so I'm talking about this. This is a picture of a Merkle tree, because you can sort of, to optimize space on the blockchain, we represent these states in form of a Merkle tree. But you can think of it as a Turing machine. So you said you have a machine. It's in state Q0. It sees a 1. So then the program, he's claiming that the program says write a 0, change to state Q1, and move to the left. If you don't know what a Turing machine is, that's fine. Just note that whatever the judge said, he noticed that it did something different than what the solver claimed it would. So it's the solver is wrong, so the challenge is justified, and that forfeit is now deposited. Forfeited. The deposit is forfeited. So now let's look at the other piece, the smart contract piece, which is sort of the crypto-economic innovation part of this project. So how do you actually ensure that this verification actually occurs, right? What if nobody shows up to take you to court? Then it doesn't really work. So how do you make sure that people actually use the court the way it's supposed to be used? So the second idea, you offer awards for checking computations. Just pay everybody for who checks. So now how do you know that they checked? Well, you go back and run the computation yourself. You checked that they checked. Well, you might as well have just done the thing yourself in the first place. So this incentivizes participation if you pay people, but it doesn't incentivize correctness. So idea 3 would be that you offer rewards for finding bugs. So this gives you correctness, but it doesn't incentivize participation when there are no bugs. So it's the opposite problem. So essentially, we have the problem that these verifiers stop paying attention if they don't expect to receive any rewards. Okay, this brings us to our final scalability idea for this talk, which we call forced errors. And that is that we're going to offer a bug bounty and provide expectation that bugs will exist. And so this is actually what TrueBit does. Occasionally, the protocol pays solvers for submitting incorrect solutions. You have to get it wrong. So the dispute resolution ensures correctness whenever forced errors are not in effect. What do I mean by that? Since you're only having maybe 1 out of 1,000 times you might have a forced error, but the idea is that every verifier doesn't know when the forced error is going to come, so they're just going to check everything. So most of the time, the verifiers think they're getting paid, and the solver thinks someone's going to watch, and therefore he gives the right answer. And ideally, if we made our compiler exactly right on this architecture, no one's ever going to go to court. This subroutine is never even going to be executed. So that's a lot of work for code that you're never going to run. Now, if you only remember one slide from my talk, please look at this one. This is a picture of an illustration of Simon de Rovier's panoptic computer, which is based on Bentham's panopticon, and which has physical manifestations in the state penitentiary in Joliet, Illinois, the Presidio Modelo in Isla de Pinos in Cuba, and it's a prison, okay? So you have, in the middle, there's a watchtower with someone who's looking around into all of these cells. There's a bright light, so they can't see what he's looking at, but out of fear that the guard sitting in the watchtower is actually looking at them, they actually behave correctly. So that's the principle of the panoptic computer. It's all about, you imagine that these people sitting up here are all performing the computations, and they do it correctly because they think they're being watched. So, and I just quote from Michael Foucault, who is also an important figure he wrote a book, in the 1970s about panopticism. We have seen that anyone may come and exercise in the central tower the functions of surveillance. So anybody can sit in there. Now, there's no reputation. This is exactly an illustration of TrueBit, because there's no reputation in TrueBit. Anyone can come in and do that. So let me, in the last few minutes, talk about the developments that we're going on with TrueBit right now. So the TrueBit virtual machine, when I speak of the virtual machine, I mean specifically this new architecture that's offside, which is part off-chain, but also your on-chain stepper, which allows judges to participate in this mechanism. So, as I mentioned before, the tasks have to compile and execute identically on all machines. Otherwise, there's no notion of step, and the judges can't really participate. So they all have to be the same. The other thing is that your single computation step on the TVM has to be running within Ethereum's gas limit itself. So into this, and not only that, you also have to, the space required to describe a state change also has to fit inside Ethereum transaction. So we ideally you'd use a Turing machine, as I said before, but there's no, at least I haven't found any code that takes a bit of C code and turns it into a Turing machine. So we had to do the next best thing, which is go to WebAssembly, and we even broke that down further. We have each WebAssembly step is broken down into basically 16 sub-steps, sort of. So we have these properties of our architecture. So if you look at what does it look like overall, the picture of the TVM. So you have your C and C++ code, and it's coming in to you want to run this task. So your smart contract needs some computational boost. So you have a C or C++ code that says the task that it wants performed, and it wants to ensure that it's done correctly. You can use this property called unscripting, which we use to transform the C++ code into the WebAssembly code. Now that WebAssembly code is used in two places. It's used both off-chain. We use the OCaml reference interpreter to generate the states, your list of computation steps that are going to go through on the computation. That's used by the solvers and the verifiers. Meanwhile, the task giver pitches this WASM task actually he commits the task to the chain itself so that it's enforceable, so the judges can do it there. And then all of this stuff about the incentives that we discussed before and the forced errors are monitored there, and we have this is what holds the money that pays out some of the incentives. And here's where the judges live. They're running, that's on-chain and it runs one step. Now I want to point out that we do have a new file system for TrueBit, which basically has, it currently has two flavors. One is, even if you store the data on the chain, you still need a file system to access it on the blockchain. So you can put your data on the chain, and the advantage there is that it stays there, but the disadvantage is you can't put very much. IPFS, on the other hand, you can store whatever you want, but data availability, well, ideally we want a system that has both of these properties. The data is available and you can put stuff there. So to be continued. So let me just wrap things up. We're in the process of one of the first applications of TrueBit is going to be the Doge Ethereum bridge, and we've got the code ready on the Ethereum side, but we need to reach out to the Dogecoin community and get them to put in the new opcode that we need, which is going to be something that allows people to take Dogecoin off the Dogecoin network and put it onto, lock it on the Dogecoin side, unlock it on Ethereum, use it in a smart contract, whatever, and then lock and unlock, send it back, it's a Doge again. And in order to reach out to people, we are instituting a new public art project. So I'm calling everyone who's interested in being part of this amazing movement. This is a once-in-a-lifetime opportunity. Come talk to me after this talk. As I mentioned earlier, we're live on Kovan testnet. And all of our code is up on GitHub. Check us out on TrueBit. Follow us on Reddit, Medium, GitHub, Twitter, and Facebook. And thanks, everybody.